So hello everyone, I'm Doyeon Kim and I'm currently a postdoc at the University of Toronto. And today I'll be talking about a project I worked on with Patrick Taylor during my time at NASA Langley. And the title is What Factors Explain the Current Arctic Albedo and Its Future Change. This is published earlier this year, so you can find additional information from the same title of this paper. So to start with some background, the Arctic is warming nearly 4 times faster than the other globe. And this figure shows historical observation in red line here and the old CMIP 6 models in colored lines here. So as you can see, all models project continued Arctic warming throughout this century. And although there is still considerable spread among the models. This rapid warming has important implications for the Arctic climate system, and one of the key feedback responsible for it is the surface albedo feedback, and which is the focus of this study. So before we get into the analysis, let me briefly explain what surface albedo is. So surface albedo is simply the fraction of incoming solar radiation, and that's reflected back to the space. So it's the ratio of upward short-wave radiation to downward short-wave radiation. For example, here the snow and sea ice have a very high albedo, around 0.8, so they reflect most of incoming sunlight. But the open ocean like here has low albedo, about 0.06, meaning it absorbs most of the solar energy. So in global warming case, sea ice melts and more open water, so surface albedo decreases, more heat uptake from the ocean side. So this positive feedback mechanism is the main mechanism to explain the Arctic warming. So here, as I earlier mentioned that the Arctic is projected to continue warming, but there is still a large spread among climate models. So where does this uncertainty come from? Is earlier paper, Piton and Morrison, 2014. They decompose all the contributors to radiative feedback contributors to Arctic warming. For example, albedo, Lapsley, Planck, or water vapor. And among them, surface albedo feedback is the largest contributor to the spread of this Arctic warming across the models. So that raises the important question that what controls the surface albedo feedback, and are current climate models representing it correctly? So here in this analysis, we compared a series satellite data with albedo surface albedo in the Arctic with CMIP and CMIP 6 model output. We used series EBAF surface albedo observation from 2001 to 2023 as our primary observational data set. And we then compare with CMIP simulations and CMIP simulation, and these CMIP simulations use the same sea surface temperature and sea ice concentration boundary. And surface albedo here define the ratio from upwards short-wave radiation to the downward short-wave radiation at the surface, and all the analysis averaged over north 65-degree and sunlit season March through September. Before looking at the albedo itself, I'd like to show why it matters. Here, we are looking at the amount of short-wave radiation absorbed because of surface albedo. And this scale, each scale represents the CMIP models, and the triangle mark represents serious satellite observations. And as you can see, there's quite large spread among the models, with some model absorbs much more or much less solar radiation than the observation. And then this large spread in short-wave radiation from the albedo related actually explain the total short-wave radiation 90%. So surface albedo differences significantly impact Arctic's total surface short-wave radiation budget. And then this on the right side is the surface albedo differences among the model, which is corresponding to short-wave radiation absorbed at the surface. And let's say we have just 0.1 differences in surface albedo, which looks like very small, but it translates to 17 watts per meter square in the Arctic area, in the small Arctic area. So it's huge amount of changes in short-wave radiation. So the relatively small surface albedo can affect whole radiative feedback and short-wave radiation budget and radiative budget in the Arctic region. The next question is what causing this spread of surface albedo? So one obvious candidate is CS concentration. And this figure shows Triple et al. 2012 Arctic September CIC extent. And red one is observation, and each colored line is CMIP models. And as you can see, they have large intermodal differences in CIC extent, and also the model shows many of them fail to reproduce the observed decline, can't reproduce the observed decline of CIC extent. So if CS concentration is the matters, then we can actually compare it with this result with AMIP simulation. So compared to CMIP simulation, which is fully coupled model, but AMIP simulation, they prescribe its model only for atmospheric only models. So it prescribes sea surface temperature and CS concentration. So all the models has same CS concentration. So I can assume that if we compare the same surface albedo, then their difference is much smaller than CMIP models, because if it is originate from the CS concentration. And these circle marks represent the AMIP simulations. So as you can see that even they prescribe the sea surface temperature and sea ice concentration, they have still considerably large amount of spread in AMIP simulation, and it also reflects to short-wave radiation as well. So that means even we reduce the uncertainty in sea ice concentration, but we can't fix the surface albedo differences. That means also surface albedo feedback and Arctic warming. So then why this is happen? So first we compared all Arctic area with ocean and land area. And for the entire Arctic, the AMIP and CMIP simulation model are very well correlated, like about 0.7. However, over the land, this agreement between much stronger, like 0.8 and 0.7, that suggests that dominant source of this spread is likely over the land rather than over the ocean area. And this figure shows land snow concentration and land surface relationship between land snow concentration and land surface albedo. And its squares are CMIP model and circles are AMIP simulation. And as you can see that models with a larger land snow concentration shows the higher surface albedo. And the correlation between AMIP and CMIP simulation are very high, land snow and land albedo, both of them. And it shows that because even the AMIP simulation, they prescribe the sea ice concentration over the ocean, but they didn't prescribe the snow cover over the land, and that all affect the surface albedo differences in both AMIP simulation and CMIP simulations. So back to this figure again. Now we understood that all these surface albedo differences in AMIP simulation from the snow cover. Then what about the ocean? So ocean itself, we prescribe the CS concentration, but we still have large disagreement in the surface albedo. then it means that CI's concentration is not a main driver for spread in surface albedo. To answer this question, we developed a simple decomposition framework that separates Arctic surface albedo into three physical components. First, we separate the Arctic region with ice region and ocean region, and ice region is defined by over 15% CS concentration region. And from this ice region can be decomposed by changes in sea ice albedo, sea ice concentration, or extend spatial variance term with ocean albedo. But we actually summarized three very important physical term, which is sea ice albedo and sea ice concentration and extent term. First, sea ice albedo term is like brightness of sea ice. So surface characteristics such as melt pond coverage, snow cover on sea ice or ice thickness. And sea ice concentration is sea ice fraction in the ice region. And sea ice extent term is how much the edge of the sea ice region is expanding or shrinking. So here are the results of this decomposition. First, you can see this surface albedo here spread with squares CMIP and circles AMIP and triangle with series. And each column represents each contributor to surface albedo differences, and summation of all these components agree almost perfectly with albedo from the models, so confirming that our decomposition works very well. So, and let's focus on the AMIP simulation first. Here is Circles 1 AMIP simulation. Remember that in AMIP simulation, sea ice concentration and sea surface temperatures are prescribed. That means difference associated with sea ice is almost zero here, like sea ice concentration, spatial variance term, or sea ice extent term is almost zero. And all these differences from the sea ice albedo term. So here, all the AMIP simulations are important results from the sea ice albedo. And this is because when we decompose albedo with sea ice concentration here and brightness of sea ice, and this sea ice albedo represent a brightness of sea ice. So sea ice albedo is not a fixed property. It changes throughout the summer melt season because of process of melting snow or pond formation on pond evolution and eventually open water. So it starts with very high albedo like 0.8 and drop to 0.2. So models have different physical representation about this Arctic sea ice albedo that affects all these differences surface albedo in AMIP simulations. And when we compare this with observation in March and September, then compared to here first row CMIP multimodal mean and second row and CMIP minus series observation albedo bias, we have models underestimate series observed albedo in the Central Arctic and overestimate surface albedo in the marginal sea ice zone. And most of this underestimation of surface albedo is actually from the sea ice albedo bias. So sea ice albedo bias is a primary factor we have to reduce in the future. And let's see the CMIP result. So compared to AMIP simulation, CMIP result, both sea ice concentration, sea ice extent term related with sea ice dynamics and sea ice configuration is very important as well to explain the spread of model. But still, sea ice albedo itself is important, likewise the AMIP simulation.
Doyeon, you've got 5 minutes.
Yeah, when we compare the series and multimodal mean, and they have good agreement in the seasonal average, But when we see the seasonal and regional analysis, it has large differences, especially in March. Blue is Turkish Sea, green one is Central Arctic, red one is Greenland Sea, and yellow one is Barents Sea. And most of surface albedo differences from the Barents Sea and Greenland Sea is all from the sea ice extent term from the marginal sea ice area. But September, later summer season, the Chukchi Sea and Chukchi Sea and Central Arctic is very important to explain spread of the models, and this from the sea ice albedo and sea ice concentration term. So earlier summer season sea ice extent term, Barents Sea, is very important, and later summer season sea ice albedo term is important to Central Arctic. So finally, I want to show some temporal evolution of Arctic surface albedo with a future scenario with SSB 245 and 585 colored line and observation and series. So following the lines here, temporal evolution of surface albedo changes closely follow the sea ice extent term. But as you can see in the Central Arctic, compared to Cirrus shows sharp decline trend until 2010 and significant fluctuation affected by sea ice albedo term here. But in the models in sea ice albedo term has a really minimal variability and compared to Cirrus observation. And this variability in the present day, 2000 to 2023, the surface albedo decline in the model is -2%, but it's almost doubled in Cirrus observation. And also ice albedo, when it shows trend, the reanalysis shows the no unrealistic flat sea ice albedo, and compared to blue line cell line observation, but black line climate model also failed to capture sea ice albedo trend observed in cell line data in this blue line. To summarize this presentation today, what factors explain the current Arctic albedo and future change? First, the substantial intermodal spread in Arctic surface albedo is not explained by sea ice fraction alone, but is largely driven by variability in sea ice albedo from our decomposition method. And second, sea ice extent term dominates the long-term albedo decline, whereas CMIP models underestimate the observed sea ice albedo variability in present day. This suggests greater future Arctic albedo variability than currently projected. I'd like to leave you with one final take-home message here. So our results show that realistically representing sea ice extent is important, but it is not sufficient. So especially sea ice albedo, its magnitude and variability is critical for reliable Arctic climate projection. Yeah, thank you very much for your attention.